All right, so let's try a simple classification task. We're going to download some data here from, this is going to be, I think, the MNIST data. Let's see which one we got here. Yep, MNIST data. Too many sessions, yeah. Manage sessions, terminate other sessions. There's some kind of limit of how much resources they'll give you on Google Colab. It's great. You can't argue with the price, but I do have to terminate my old sessions now and then. All right. That's going to download another standard machine learning training data set and print a description of it. And it's still running. It shouldn't take too long. 21 seconds. There we go. Okay, so the MNIST data set is handwritten digits. These are digits written by, I think, American census takers. And so they're digits, and they've labeled them with what the real digit is. And so you have a bunch of images. Each one of them is 784 pixels of grayscale. And there are 70,000 images. And you have the images themselves, and then you have the labels. The first one's a 5, next one's a 0, next one's a 4, and so on. So that's what we have, 70,000 records. And we can view some of them to get an idea how they look. There you go. That's what they look like. Handwritten digits. And you know what the right answer is, 504. And this one, not entirely clear if it's a 3 or a 5, and so on. And here you got a funny artifact in the edge of the corner, but we haven't cleaned that out. So we're going to train it on these real images. And like I say, for discussion in the previous project, I probably would have preferred to clean this off because that's not part of the digit. But anyway, that's what we have. That's the training set. So we break it into a training set of 60,000 images, and we're going to have 10,000 left over as the test set to test our model. All right. So now we're going to make a binary classifier. And what this is going to do is it's just going to tell if it's a 5 or not a 5. Instead of sorting it into 10 categories like we did before, we're just going to make a binary classifier. Is it true or false that the digit you're looking at is a 5? All right, and so and this trains it. Why train? Well, this just counts how many true. So that in both sets, there are the number that are true is 5,000. The number that are false is 50,000 because they're equally distributed across the digits and the test set. So this is just the data. And so 90% of them are not 5, 10% of them are 5, of course. Now we're going to make a model, a simple linear model like before. Take the pixels and just treat each pixel as an independent measurement, and we're just going to converge on one neuron from the pixels. Once again, as someone that did real brain models for the human brain and vision, I rebel at the fact that you did even retain information about the fact that there's a line here and these things are next to each other and this is all background. But it's another stupid model. It treats each pixel as just independent data. So now we're going to make a model here, and this is going to be a stochastic gradient descent classifier. As before, make a simple model from sklearn, and it's going to go through some epochs of training. Here's the loss going down, 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 as before, 500, 400, 300. The loss is, just a measure of how many of them it got wrong, 200, 180. And I think this one is down to 115, 107, 96. Okay, this does, now you might have wondered, we talked before about doing 5 rounds of training, 500 rounds of training, and you might wonder how much training to do, and this is one way to do it. You just keep training, you do epochs until it starts getting worse. Well, that would mean you hit the bottom. You hit the bottom, and now it's getting bad again. That's what this did. That's why it stopped at this funny number, 239 rounds. See, the loss was going 78, 78, 77.6, then 77.8. As soon as it starts going up, well, apparently you hit the bottom. Then you stop. That's one way to do it. So no point training more. That would be overtraining. So here we are. So now we predict the first few images. It gets the first one is 5, and it says it's true. The next 2 are not 5, and it says they're not 5. So the first 3 images, it got it correct. Now we can measure accuracy. And we're going to do it with cross-validation. We split the training data into three folds, train it on two-thirds of the data, and predict the other remaining one-third. And we do that three times. This is called cross-validation. It's one way to measure the accuracy of your model. And so now it's going to have to train three times. And we're going to get accuracy measures of 95%, 96, and 96%. You'll see them down here when it's done. And that sounds good until you remember 90% of the data is not fives. So if you just say false all the time, you'll get 90% accuracy. So 95% is not as great as you might think it is. Anyway, you can also express the result as confusion matrices that give you a more complete measure of what it did. I'll get the next one ready to go here. There, that previous one finished. So there you are, 95%, 96%, and 96%. Those are the cross-validation tests of accuracy. Here's the confusion matrix. Again, it's going to train the model. I could probably rewrite this so it doesn't keep retraining it so often, but it doesn't take long. Just let it go. So we're going to get the whole confusion matrix, and I'll just go here and show you. This is the first row is the non-5 images. So it correctly called 53,000 of the non-5s not 5, and incorrectly called 687 of them equal to 5. And here's the 5s. It correctly identified 3,500 5s, but it said they were not 5, 1,891 at a time, which is pretty bad. So that's a more complete description of the accuracy of our model. And there are various measures. Precision is true positives over true positives plus false positives. This thing called recall is true positives over true positives plus false negatives. And there's a thing called the F1 score, which is precision times recall over precision plus recall. That's a number that will, if it's 1, you have a really strong model. If it's less than 1, then your model is making mistakes. And there are situations in which you would like more precision or like more recall. And you can predict them, and you can even get the trade-off, because what happens is the model doesn't really report true or false. The model just reports a signal, and the signal has low to high values, and you can choose what threshold it is. So if you make the threshold low, it will more often interpret it as true. If you make the threshold high, it will more often interpret it as false. So you can make a neuron output signal from this. The default is to just say anything above 0 we're going to call true, and anything below 0 we're going to call false. But you could change the threshold to different levels. And so here we're going to make, here's the chart I wanted to show you. You can just adjust the model. And if you've done like CISSP training, the same thing's true of biometric classifiers. If you have something like a fingerprint reader, you can set it to be really sensitive so the fingerprint has to exactly match, and then you'll have very few unauthorized people that get through, but you'll have more authorized people that are rejected because it doesn't like their fingerprint. Or you can make it the other way, where it's very tolerant, and then the authorized people will always get through, but more unauthorized people will get through. And that's essentially the same thing here. So once you've trained the model, you can then move the threshold for how big a signal you would require to give a result of true. And we'll see a graph coming up here pretty soon. I'll just go to the right answer here. There's the graph. As you move the threshold, you have precision and recall. If you move it down to, you maximize one of them or maximize the other, and the crossover point is near 0, where the two are equal. And up here you get some noise because you're reaching the point where there's essentially nothing ever considered true, so the number is very small of ones that are accepted. So that's a thing to know about this. And now we can make a support vector machine here, which I'm going to talk about more in a minute, and we can make a multi-class model. So since all you have is a binary classifier, how do you sort things into 10 categories? There's 2 techniques. You can do 1 versus 1 or 1 versus many. This is going to do 1 versus 1, so it makes 45 separate binary classifiers. 5 and not 5. And I don't remember exactly how you get to 45. I think by comparing, now Yeah, it's five and not five, one and yeah, I forget. It's in the book. I forget how you end up with 45. Um, I think you compare just pairs. Uh, anyway, this is a way to to combine these binary classifiers. And it's one versus one, right? You compare, is it 0 or 1? Is it 0 or 2, 0 or 3? How you get 45. You compare individual digits, and there's 45 possible combinations there. Uh, that's what it is. And so by combining them all, um, the first column is the right answer, and the second column is true if it was correct and false if it was not. So out of what I did was I tested 100 random samples and only got three of them wrong after all this training. So these are the only three it got wrong. It was supposed to be a 9, and here's the signal, and the largest signal is 8 here. No, this is the 9, but there's a larger sample here. So it should have been a 9, 8, but it actually decided it was a 6. And this one should have been a 1, but it looks like it had a stronger signal for 2. And this one should have been a 9, but it had a stronger signal for 8. So those are the three it got wrong out of 100 test images. And now one versus the rest is the other way. You do 0 or not 0, 1 or not 1, 2 or not 2, and then you combine those. So it's only going to have 10 classifiers now, but the classifiers are going to be, all in a situation where 90% of the answers are false. These are just two ways to combine binary classifiers to categorize into 10 categories. And this time, it's only going to get two of them wrong. All right. So you can you can train a model to classify it, and then you can also see the overfitting. Um, and then we can get to the cross-validation. And the confusion matrix is the last thing I wanted to show you. This is a full representation of the accuracy. Here's the predicted label and the true label. So the accurate ones are on the diagonal and the errors are elsewhere. And as you can see, the errors are not evenly distributed at all. If you have a real 9, it has a high chance of interpreting it as a 4 or a 7. And if you have excuse me, if you have a real 1, it has a high chance of misinterpreting that as an 8 for some reason. So anyway, this is the way you uh, describe the actual performance of your model, and there are some other things there to try. So that's a little bit of statistics. Let me stop this one.